Physical change. We're going to talk about physical change and chemical change. So what we mean by a physical change is that it may alter the state, solid, liquid, or gas. It may alter the appearance, but it's not going to affect the individual molecules or atoms that the substance is composed of. So the example given here is boiling water. So here we have water boiling. This is what the water looks like in the liquid state. These always remind me of Mickey Mouse, little Mickey Mouse heads. The red oxygen and the white hydrogens. So you have all these little water molecules. They're very close together. They're swimming around in the liquid phase. When we boil it and it becomes a gas, the individual particles of water, the molecules, look exactly the same. Just like when the liquid state of students in labs leaves through the door and goes into the gas state. Does it change how you look out there? Does your hair color suddenly change? An arm falls off? No. You're the same. It's just your interaction with the other particles with your other students is different. So in the gas state, the particles are not interacting with each other and they're just going off in all directions. But the particles themselves were not changed. That's a physical change. Take a piece of wood, cut it in half. It looks different. Its mass is different. It's two pieces now instead of one. Did you change the particles that the wood is made of? No. It's just a physical change. In a chemical change, the composition is altered. The individual particles are messed up. We think about rusting. Iron rusts, right? So here's an iron nail, and as the rust forms on it, it's this reddish stuff, and it's flaky and crusty, right? It's not as strong as iron. If we look at what's going on the particulate level with the atoms, so here's the iron atoms, and they're attached to each other in this nice crystalline solid. They're very strong. When it rusts, oxygen gets incorporated in between the iron atoms, and it expands. It's going to get a little bit larger because the oxygen has come in there. The color is going to change, and it's not going to be as strong as it was. It's weak and flaky now instead of shiny and strong. So the atoms got rearranged. The original atoms are still there. They didn't get destroyed, but now they're interacting with oxygen as well, and so the particles have been changed. A couple more examples. So this is a physical change, dry ice subliming. So here's dry ice it's just held in a ring there. It's just a big chunk of dry ice. Dry ice is carbon dioxide in the solid form. So this is what the little carbon dioxide molecules look like in that solid dry ice. We've got the black carbon in the middle and two oxygens, two red oxygens. Dry ice does not melt. It goes directly to the gas state. That's why it's called dry ice. Regular ice is wet ice. It melts. But carbon dioxide doesn't melt. It just goes directly to the gas. And so as this goes into the gas state, the molecules are the same. Really don't know why it's doing that. The molecules are the same. Maybe I should just point up there. But they're further apart. The molecules are the same, so it's a physical change. Okay? Sugar dissolving. We talked about putting sugar into tea, right? So here we have the chemical formula for sugar. And when we put it into water, so here's the solid sugar, and that's what the molecules look like. When we put it into water, the individual molecules are going to come away from each other, but each of those molecules is going to look the same. So the molecules have not changed. They're just separated from each other. It's a physical change. It's still sugar. If you take this solution of sugar water and evaporate all the water out, you're going to still have sugar. Okay? It's a physical change. This is an example of a chemical change. Propane burning. So here's a little propane tank with a burner on it. Here's the propane. The formula is C3H8. We'll learn more about that later. But the molecules look like this. There are hydrogen and carbon. When the propane burns, it combines with oxygen from the air, and it forms carbon dioxide molecules and water molecules. These individual particles of the substance are very different from the original particles. The particles have changed. It's a chemical change. Any questions? So those were changes. We can also talk about physical and chemical properties. So a physical property, the substance displays that property without changing its composition. So these are things that you can measure or observe without destroying the stuff. So gasoline has a distinctive odor. When you smell the gasoline, does it change what the gasoline is? No. You're just observing how it smells. The taste of something, the color of something, its appearance, melting point, boiling point, density, those sorts of things. When you determine the physical property, you don't destroy the substance. A chemical property is one that the substance displays only by changing its composition. A chemical property is essentially a description of a chemical reaction. So gasoline is flammable. That's why we put gasoline in our engines, because we want it to combust inside the engine. We want it to burn. When you demonstrate the chemical property that gasoline is flammable, you have to burn the gasoline, and now it's not gasoline anymore. Corrosiveness, acidity, toxicity, those sorts of things are chemical properties. Any questions? Okay, so what kind of things should you be able to do with this knowledge? You should be able to answer a question like this. Determine whether each change is physical or chemical, and what kind of property, a chemical or a physical property, is demonstrated in each case. Okay, so a copper wire is hammered flat. So picture this, you take a copper wire and you take a big hammer and you bang on it and you flatten out the wire. Does that change what the copper wire is made out of? No. It changes its shape, but it doesn't change what it's made out of. So is that a chemical change or a physical change? It's a physical change. So that's a physical change. That property is called malleability. Metals are malleable. You can take a piece of metal and you can hammer on it and you can flatten it. Many other substances are not malleable. Is glass malleable?
No.
No. You hit glass with a hammer and it will just shatter into lots of little pieces. Metals don't do that. So that property is a physical property. Okay? Letter B. A nickel, the coin, dissolves in acid to form a blue-green solution. That's going to be a chemical change. So the nickel is actually, originally was made out of nickel metal. It's got nickel atoms in it. When you put it in the acid, it's going to change color. And now you've got a blue-green solution. The nickel itself, you can't see it in there anymore. So the nickel atoms, what's happening is they become ions and they go into the solution and they cause the solution to have a pretty blue-green color. But the original nickel atoms aren't there anymore. They've been changed. So that's a chemical change. The property that nickel dissolves in acid is a chemical property. Does that make sense? Dry ice sublimes without melting. That's a physical change. It's kind of funny that they put this one in here because we just looked at a picture of that. It's a physical change. The property we're talking about here is that dry ice sublimes. Is that a physical property or a chemical property? It's a physical property. You can demonstrate the property without destroying the dry ice, without destroying the particles. They become a gas, but you could make them back into the liquid. When you demonstrate this property that nickel dissolves in acid, you have destroyed the original substance. You don't have nickel atoms anymore. How about a match ignites when struck on a flint? That's going to be a chemical change. You strike that match, you get a flash and some smoke and a flame, right? Afterwards, look at the match in your mind, because I don't have a match right here. I should get a match, because that would be an excuse to light things. I do like fire. But it's changed. Does the match do that again? Can you use a match over and over again? No, that's a one-shot deal. That's a chemical change. And that chemical change is observed when we demonstrate the chemical property. Matches igniting when struck are a chemical property of the matches. Something like the color of the match would be a physical property of the match. You can demonstrate the color, hey, look, this match is red, without destroying it. But to demonstrate the chemical property, you've changed it. Okay?